Hey guys, welcome to Chem SM. So we're going to be starting with the bond angles. So let's take a simple example of SF2. I'm just going to be drawing the Lewis structure. So this is the structure of SF2. As you can see, it is bent 4. Since it's bent 4, we know it will have an angle of 104.5. The simple way to work this out is take the basic angle of 4 regions of -t, as it has 2 bonding pairs and 2 lone pairs. And since it has 4 regions, that's 109.5. 2 lone pairs, just subtract a bit. So why is it not actually 109.5? This occurs due to the lone pairs that are on the central atom, sulfur. These lone pairs have a stronger repulsion, which pushes these bonds further away. So now the bond angle between the 4 is now smaller to 104.5 from the original 109.5, which you would find if in, for example, methane. So now we'll be moving on to intermolecular forces, also known as the van der Waals forces. The weakest one, as you can see, is the London dispersion force. This also tends to be the most common. For example, in BR2, the only thing holding these two covalent molecules together is an induced dipole. This happens when enough electrons are on one side of the atom, of the molecule, to create a slight negative charge here and a positive charge here. This negative charge will cause the electrons over here to move to this side as they are repelling, creating an induced dipole of a positive charge here and a negative charge here. This positive and negative charge then attract, bringing these atoms closer together, which is why bromine is a liquid at room temperature. The general trend across the periodic table is the bigger the atom, such as bromine, iodine would have a greater melting point because there are more electrons, creating stronger dispersion forces. That is the gist of dispersion forces. The next type of van der Waals force is the permanent dipole-dipole. This occurs when there is when the molecule is polar, causing a permanent dipole. For example, in HCl. In HCl, the chlorine is a lot more electronegative than the hydrogen. So the electrons spend most of their time around the chlorine, creating a permanent negative dipole here and a positive dipole over here. This will then attract to the next hydrogen chloride, which will have a positive dipole here, and a negative pole over there. These then attract. And similarly on this side, you also have another Cl negative. Be aware these aren't covalent bonds. These are just electrostatic attraction. And then you also have, and this chain can repeat in all directions to form the bonding, the intermolecular forces in the form of permanent dipole-dipole in polar molecules. And then the last type of force is a hydrogen force. This is special and only occurs with oxygen, nitrogen, and fluorine. This occurs when these 3 elements, and only these 3 elements, are bonded to a hydrogen atom. For example, in H2O, in NH3, in ammonia, and in hydrogen fluoride. Here, the electrons are a lot more strongly attracted to the oxygen due to the very high electronegative difference between the 2 atoms. And now, since this is a lot stronger here, you have a lot stronger negative charge than you do in a dipole, and a lot stronger positive. And similarly, these attract to other ones, and the attraction is much stronger, which is why the hydrogen bonding is the strongest out of all 3 intermolecular forces. So now polarity. Polarity can occur in 2 different situations. The first one is when there's an electronegative difference between the 2 molecules, which is greater than 1.7. And this can easily be seen in examples such as HCl. The electronegative difference between these 2 atoms is greater than 1.7, and the electrons are very closely attracted to the chlorine. And therefore, this is just generally polar. However, similarly, you could argue, then why is BF3 not polar, as the fluorine is a lot more electronegative than our boron atom? This is due to the overall shape of the atom. Since it is trigonoplanar due to the 3 regions of negativity, there's a negative dipole here, here, and here, And since they're all equally negative, there is no overall charge on BF3. Therefore, due to the symmetry of the atom, this makes it not polar. And then using these two concepts, you can see with H2O, where even though it may seem symmetrical, as there's two areas, here each of these, this one, this side would be negative and these would both be positive, since it is bent and not symmetrical, it does result in a polar molecule in H2O, as the positive is towards the lower side and negative towards the top side. So this would be polar. So when explaining polarity, you have to refer to these two situations. If this is the case, that is the most prominent reason for polarity, and if that is not the case, if that does exist, yet the molecule isn't polar, it's due to the symmetry of the molecule.